Implicit differentiation. Consider the function y equals the square root of x. To find dy dx, we can proceed as normal. So y equals the square root of x can be rewritten as y equals x to the power of a half. So dy dx, the derivative, is going to be a half x to the power of minus a half. Because we bring the half down in front to bring the power down in front, and we reduce the power by 1. A half minus 1 is minus a half. And next we simplify. So since we have a negative power, that gives us the reciprocal, which is 1 over. Since it's to the power of a half, this is really the square root. So we have 1 over the square root of x. And since we're multiplying that by a half, for fractions we multiply top by top, bottom by bottom. So it would be 1 multiplied by 1, which would be 1. And it would be 2 multiplied by the square root of x, which would be 2 root x. So we get 1 over 2 root x. So if y is equal to root x, then dy dx is equal to 1 over 2 root x. Alternatively, we can write y equals root x as y squared equals x. So basically we're bringing the root over the equal sign and we have y squared equals x. Now we can differentiate each term on both sides with respect to x. To differentiate y squared with respect to x, we have to use the chain rule. This technique is known as implicit differentiation, as y, wherever it occurs, is an implicit or implied function of x. So y is equal to the square root of x. Therefore, y squared is equal to x. So we want to differentiate y squared with respect to x. So dy squared dx means to differentiate y squared with respect to x. And on the right hand side of the equal sign, we have x. So we want to differentiate x with respect to x. So dx, differentiate x with respect to x. So in order to differentiate y with respect to x, or in this case differentiate y squared, we must use the chain rule. So this becomes dy squared dy multiplied by dy dx. So we're basically breaking this apart. The numerator stays on the left and it's over dy. And the denominator goes to the right and we have dy on top. So basically what you're doing is you're multiplying above and below by dy, so you're not actually changing the value of it. And then dx, so differentiate x with respect to x, we just get 1. Okay, so dy squared dy, so to differentiate y squared with respect to y gives us 2y. So the derivative of y squared with respect to y is 2y. We bring the power down in front, the 2 comes down in front, we reduce the power by 1, 2 take away 1 is 1. So you get 2y to the power 1 or just 2y. This is multiplied by dy dx, so we just leave dy dx as it is, and this is equal to 1. Okay, so we want to get dy dx on its own. We want to solve for dy dx. So we need to bring the 2y over the equal sign, and it becomes 1 over 2y. So technically what you're doing here is you're dividing both sides by 2y. And what happens is the 2y on the left cancels, so you're just left with dy dx, and you have 1 over 2y on the right hand side. So we have dy dx equals 1 over 2y. So differentiate y with respect to x equals 1 over 2y. But we know that y is equal to root x. So we end up with 1 over 2 root x. So where did we get this from? Well, we stated at the start that y was equal to root x. And so therefore dy dx, the derivative of y with respect to x, is 1 over 2 root x, as we worked out on the previous slide. When implicit differentiation is used to find dy dx, the answer may contain y as well as perhaps x. Unlike in the example above on the previous slide, it may not be possible to remove the y. Implicit differentiation can be used to find dy dx from any curves in the plane, even when they do not represent y as a single function of x. So for example, the equation x squared plus y squared minus 2x plus 6y minus 3 equals 0 represents a circle And implicit differentiation can be used to find dy dx, i.e. the slope of the tangent at any point on this circle. The following example shows how to use implicit differentiation for a curve such as this. Find dy dx, so the derivative of y with respect to x, for the circle with the equation x squared plus y squared minus 2x plus 6y minus 3 is equal to 0. And hence, so using the derivative of this function, find the slope of the tangent to the circle at the point 4 minus 1. So, in order to work this out, we have to differentiate each term on both sides with respect to x. So, if we are given x squared, the derivative of x squared with respect to x is 2x. We bring the power down in front, so we get 2, reduce the power by 1. 2 taken by 1 is 1, so we get 2x. Now, if we want to differentiate y squared with respect to x, we bring the power down in front, so the 2 comes down in front. We reduce the power by 1. 2 taken by 1 is 1, so we get 2y, but we have to stick on a dy dx. If you're unsure of why we did this, it's because of the chain rule, and you can look back on the previous slide to see why we did this. But basically, if we're differentiating a y term with respect to x, we have to stick on a dy dx. Next, we want to differentiate minus 2x with respect to x, so we just get rid of the x, so we have minus 2. And next, we want to differentiate 6y with respect to x. So 6y to the power of 1, we reduce the power by 1, so we just have y to the power 0, which is technically 1, and 6 multiplied by 1 is 1. So you just get 6, so technically what you did was you just crossed off the y. But again, because we're differentiating a y value with respect to x, we stick on a dy dx. And again, if you're not sure why, it's because of the chain rule, and look back to the previous slide to see why. And then to differentiate minus 3 with respect to x, well, we just get 0. So when we differentiate a constant, we always get 0. Now, rearrange the terms to leave all the dy dx terms on one side and all the other terms on the other. Then isolate dy dx. So we have 2y dy dx, so that's already on the left, so that can stay there. And we have 6 dy dx, so again that can just stay where it is, so the signs do not change. Then we have our equals. So we're going to bring this 2x over the equal sign, it becomes minus 2x. We're going to bring this minus 2 over the equal sign, it becomes plus 2. So we have 2y dy dx plus 6 dy dx equals minus 2x plus 2. We're going to factorize. So we have dy dx common to both, bracket 2y plus 6. And again, that's equal to minus 2x plus 2. So remember, we want to isolate the dy dx, so we have to divide both sides by 2y plus 6. So we end up with dy dx equals minus 2x plus 2 divided by 2y plus 6. Next, we simplify. So we can see we have a common factor of 2. So 2 can divide into all 4 terms, and that's important when we're simplifying. Since we have 4 terms, we have minus 2x, we have 2, we have 2y, and we have 6. We have 4 terms. In order to simplify or divide into the fraction, we have to divide each term by the same number. So minus 2x divided by 2 is minus 1x or minus x. 2 divided by 2 is 1. 2y divided by 2 is y, and 6 divided by 2 is 3. So dy dx is equal to minus x plus 1 over y plus 3. So we found dy dx. Now, hence, we want to find the slope of the tangent to the circle at the point 4 minus 1. So we take our derivative, minus x plus 1 over y plus 3, and we sub in an x value of 4 and a y value of minus 1. So we get minus 4 plus 1 over minus 1 plus 3, which gives us minus 3 over 2. So the slope of the tangent at the point 4 minus 1 is minus 3 over 2.